The Boeing 737 MAX disasters killed 346 people. The root cause? A flawed control system that couldn't properly handle feedback. Today, I'm breaking down PID controllers, the hidden technology that keeps airplanes stable, factory processes running, and yes, even your home thermostat working smoothly. By the end of this video, you'll understand why this matters way beyond engineering classrooms. Let's start with a problem you've probably experienced. Imagine a cheap thermostat set to 70 degrees. When the temperature drops below 68°F, it turns the heater on full blast. When it reaches 72°F, it shuts off completely. Simple, right? But look what happens. The temperature swings wildly between 66 and 74 degrees. You're either freezing or sweating. This wastes energy and creates uncomfortable conditions. Now scale this up to a chemical reactor or jet engine. Those wild swings? They can cause explosions or crashes. We need something better. Here's the solution engineers developed: feedback control. You set your input, let's say 70 degrees, the controller sends signals to your system. The process, your heater, responds. A sensor measures the actual temperature. This feeds back to the controller, which compares it to your set point. This creates a loop that constantly adjusts. But here's the key. Not all errors are the same. Every control system faces three distinct challenges: current deviation, how far off you are, right now accumulated drift, small errors adding up over time, rate of change, how fast things are changing. Simple controllers can only handle one of these. PID controllers handle all three at once. That's what makes them revolutionary. PID stands for proportional integral derivative. Think of them as three teammates working together. P, proportional control. The P component reacts to your current error. Room at 68°F. When you want 70°F, it pushes harder proportional to that 2-degree gap. But watch what happens. It never quite reaches 70 degrees. It settles at 69.5°F because it can only push hard enough to match heat loss. We call this steady state error. I, integral control. The I component is like a memory system. It accumulates all past errors and keeps adding correction until you hit exactly 70 degrees. This blue area shows errors building up over time. The integral component eliminates that steady state error we saw earlier. But there's a catch. It overshoots. The correction keeps building even after reaching the set point, pushing temperature above 70 degrees. D, derivative control. The D component predicts the future. It looks at how fast temperature is changing and applies the brakes. See the red line without derivative control? It oscillates. The orange line with derivative control? Smooth landing, no overshoot. When you combine all three, P gives you immediate response when something changes. I eliminates long-term drift and ensures you hit your target exactly. And D prevents overshoot and keeps everything stable. This combination powers chemical plants maintaining reaction temperatures within 0.1°F. Aircraft autopilots keeping planes stable through turbulence. Medical ventilators delivering precise oxygen to ICU patients. Your car's cruise control holding steady at 65 miles per hour. Anywhere precision and stability matter, PID controllers are working behind the scenes. So the next time you adjust your thermostat, remember, you're using the same fundamental technology that keeps jumbo jets in the air and chemical plants from exploding. Understanding PID controllers isn't just for engineers. It's about understanding how we've automated the world safely. If this helped you understand PID control, hit that like button. Subscribe for more engineering concepts explained clearly. Drop a comment if you want me to cover how engineers actually tune these controllers to get the perfect response. Thanks for watching. See you in the next one.